Hi everyone. Today we're focusing on chemical reactions, which are changes that create new substances. So chemical reactions are happening all the time in daily life. Cooking food, burning fuel, rust forming on metal, and even digestion in your body. So the goal of this lesson is to learn what a chemical reaction is, how to recognize evidence that one occurred, and how we represent reactions using chemical equations. By the end, you should be able to tell the difference between physical and chemical changes, identifying reactants and products, and understanding why balancing equations matters. So before we talk about chemical reactions, we need a quick reminder. So matter is anything that has mass and takes up space. So even if you can't always see it, like air, it still counts as matter because it has mass and it occupies space. This definition is important because chemical reactions don't create matter out of nothing, and they don't make matter vanish. They just rearrange the matter that already exists. So here's a key question. What do we call the study of matter and how matter changes? Because if we're studying reactions, we're also studying matter. And so the answer to that is chemistry. So now we're going to separate two ideas, physical properties versus chemical properties. A physical property is something you can observe without changing the substance into something new. A chemical property describes how a substance can change into other substances, meaning how it reacts. So if you measure color or texture, that's physical. But if you describe how something burns or rust, so anything that changes the molecular formula or the chemical formula, that is chemical. So what are some example of physical properties? So some common physical properties include temperature, color, hardness, texture, shine, and flexibility. For example, ice melting at 0 degrees Celsius is a physical change. It's still water, just in a different state. So it's still two hydrogens and one oxygen. So physical properties help us describe matter, but they don't tell us how it reacts. Now, what are some examples of chemical properties? So these describe how a substance behaves in a reaction. Again, if the substance changes into something new, then you're observing a chemical property. So here are some examples of chemical properties: gasoline reacting with oxygen and burning, releasing energy; baking soda reacting with vinegar and producing carbon dioxide gas; iron reacting with oxygen to form iron oxide, which we call rust; paper burns and turns into ash, carbon dioxide, and water vapor; bleach removes stains because it breaks chemical bonds and pigments, and so on and so on. A lot of these chemical reactions are happening, uh, but in summary, these chemical reactions are called that because they form new substances. So the atoms are still there, but they've rearranged into new combinations. So this is a classic example of photosynthesis, which you may or may not have heard of, um, where we start off with carbon dioxide and water and end up with glucose, which is a type of sugar, and oxygen. Right. So if you count the number of carbons and oxygens and hydrogens, it's going to be the same amount on the left side, which is the reactant side, and the right side, which is the product side. So what does it mean to have a chemical change, right? And so chemical change means that is when chemical changes occur when bonds break and new bonds form. So that's what a reaction really is. Atoms disconnecting from old partners and reconnecting in new ways. So the diagram here shows that you can start with certain molecules, break their bonds, and end with new molecules that have different structures and properties. And on the other end, we can also form bonds. And so different chemical bonds can drastically affect properties. So the slide here shows why bonding matters so much. And for example, magnesium metal melts at about 650 degrees Celsius, but magnesium oxide melts around 2800 degrees Celsius. That's a massive difference. And even though both substances contain magnesium, the way atoms are bonded changes everything about the material's properties, like melting point and its stability. And so chemical reactions involve two main kinds of changes that you can observe. So the formation of new substances and changes in energy. So these pictures show common chemical changes: fireworks, frying eggs, photosynthesis, burning wood, combustion of propane, and digestion. So in every example, the starting materials are converted into new substances, and energy is either released or absorbed during the process. Now that we know what reactions are, we need a way to describe them clearly. Scientists don't usually write reactions out in sentences. Instead, we use chemical equations, which are like a shorthand language for reactions. So what are chemical equations? So a chemical equation is a short, easy way to show a chemical reaction using formulas and symbols instead of words. Reactants are written on the left side, products on the right side. And the arrow here means yield or produces. So a reactant yields or produces products. Okay. So chemical equations make it easy to see what you start with and what you end with. And so, to balance an equation, we go back to the law of conservation of mass. So, as we stated at an earlier unit or an earlier lecture, we stated that matter is not created or destroyed, only rearranged. So that means the total number of atoms of each element must be the same on both sides of the equation. Balancing means that the equation needs to represent a real reaction. These atoms don't just go off into nowhere or disappear out of nowhere. They're only rearranged. So this slide explains a common confusion. So subscript tells you, for example, here for glucose, subscript tells you how many atoms are in one molecule, and the coefficient tells you how many molecules you have. Right? And then so, for example, for glucose here, this glucose molecule has 12 hydrogens, 6 carbons, and 6 oxygens. For this oxygen molecule, it has 2 oxygens. But you can see here that it has a coefficient, meaning that there's 6 O2 molecules and overall 12 oxygens here. Okay? So this formula, right? So C6H12O6 for glucose, O2 for oxygen, CO2 for carbon dioxide, H2O for water. It's a symbolic representation of a chemical substance, so one molecule of that substance. Okay, now we go to this question. How do we balance this equation? Right, so we have N2 plus H2 yielding NH3. So the first step is to write the equation and count the atoms on each side. So here we have 2 nitrogen atoms and 2 hydrogen atoms. And here we have 1 nitrogen atom and 3 hydrogen atoms. Right? And so what we need to do is try to match the left side, which is the reactant side, with the product side. And then so this is essentially what we do. So in order to balance this formula, we put a 2 in front of the NH3, giving us, if we do the multiplication for this one, we're going to have 2 nitrogens and 6 hydrogens over here. And then if we look at this side, we don't need to add a coefficient for N2 because it's already matching 2 over here. And then if we want to, now we want to make sure that these hydrogens match up. And so since we have 6 total here, 3 times 2 is going to equal 6. Okay. All right. What about this one? So hydrogen plus oxygen forms water. Right. And on the left, we have 2 hydrogens and 2 oxygens. And here we have classic H2O, which has 2 hydrogens and 1 oxygen. So the hydrogen already matches, but the oxygen doesn't. So we want to be able to match the oxygens instead. Okay. And then so to do that, all we need to do is put a 2 in front of this hydrogen, this water molecule, and then another 2 in front of this hydrogen. By doing that, if we do the calculations, we have 4 hydrogens and 4 hydrogens here. So 2 times 2 and 2 times 2. And then since we don't want to change the oxygen because we already have 2 here and then 2 here. So we're not going to add a coefficient over here. And so this is another example of iron oxide. So it's a little bit more complicated. So I encourage you to look at one side of the reaction and look at the other side of the reaction and compare the amount. All right. So here's the strategy to balance these equations. So first, we want to write the equations, then count the atoms of each element on both sides. Third, use the and we use the coefficients to balance the atoms. And finally, we look back and check our work. If the atoms count, uh, if we count the atoms for the reactants and the products, and that the equation is balanced, we are following the conservation of mass.